Hello. Welcome to this lecture series on pattern recognition and applications. In our previous class, we have started discussion on probability density estimation, and the reason why we had to go for this topic of probability density estimation is that though we can have analytical expressions of probability density function in certain cases, where the analytical expression will use some number of parameters, and depending upon the kind of density that we have different types or different number of parameters. So, if I want to have an analytical expression of the probability density function, I have to know beforehand that what is the parametric form the probability density function will take. And if I know what is the parametric form or what are the parameters, then I can go for maximum likelihood estimate for the values of those parameters, or I can make use of some other technique to obtain the best possible values of those parameters from the training set of samples which are given. But if the number of samples are very limited, in that case the estimated value of the parameters are not very reliable or not very suitable, or in some other case we may have the problem that the parametric form is not really known. We do not know that how to describe the probability density function as represented by the set of samples which are provided. Okay. So, from those set of samples we cannot really estimate what are the parameters or which parametric form the probability density function has to take. So, unless we know the parameters, we cannot obviously estimate the values of those parameters. So, we have gone for the probability density estimation from the given set of training samples without assuming any parametric form of the probability density function. So, obviously, in this case I cannot have any analytical expression, but the probability density estimate that we will get, that will solve our purpose so far as pattern recognition application is concerned. So, in order to do that, what we have said in the last lecture is something like this. If I take a single variable, say x, for which I want to estimate the p x or probability density function of x. Then first what I have to do is I have to know that what is the range of values of x, that is what is the minimum value of x and what is the maximum value of x. So, if I know the range of values of x, then that range is divided into a number of intervals. Okay. And we have said that every interval is called either a cell or a bin. So, what we have done is, suppose this is the minimum value of x, or let me put it as x min, and this is the maximum value of x that I can have, say x max. So, this range of x is divided into a number of intervals. And each of this interval is called a cell or a bin, right. So, now suppose to estimate this probability density function, you have been given certain number of samples of x. So, suppose the total number of samples I have is capital N, and I take any bin, say jth bin, and I try to find out that out of this total number of sampled values of x, how many such samples lie in this jth bin. So, if the number of samples that lie in the jth bin is given by n j, then I assume that this ratio of n j by n gives me an estimate of the density of the probability density so far as this particular bin jth bin is concerned. So, this has to represent, so this represents an estimate of the probability density function in this jth bin. And I also assume that in a particular bin the probability density is uniform. So, what I will have is a probability estimate something like this. So, within this jth bin the probability density function is uniform. I can have different values of this probability density function in different bins. Okay. And I also have another constant that if this probability density function that I am estimating, it has to approximate a continuous probability density function, then the area under the probability density function has to be equal to 1. That means, the sum of the areas of all these bins has to be equal to 1. So, that clearly says that area of this particular area under this probability density function has to be equal to n j by n, because sum of n j by n, if I take the summation over all values of j, that is equal to 1. So, given this, if the width of this jth bin is equal to say w j, I have to find out what is the height or the value of the probability density function for this jth bin. And as I have said that the area has to be equal to n j by capital N, where n j is the number of samples which are falling in this jth bin and capital N is the total number of samples that I have. So, the area of this jth bin, if I call it as A j, that has to be equal to w j, which is the width of the jth bin, and h j, which is the estimated probability density function so far as this jth bin is concerned. So, this area A j has to be equal to w j times h j, and which is nothing but n j by capital N. So, from this I can have what is the value of h j, which is nothing but estimate of the probability density so far as this jth bin is concerned. So, I get the value of h j, which is nothing but n j upon w j times capital N, where this w j is the width of the jth bin, capital N is the total number of samples that I have, and n j is the number of samples out of this total number of samples, the number of samples which falls under this jth bin. Okay. So, this is how we can estimate the probability density function. And once I estimate the value of h j for all values of j, that means, for all the different bins I can have estimated values something like this. Now, for an unknown x, say x 1, if I find that this x 1 falls in this bin, the probability p of x 1 will simply be given by this p of x 1 is nothing but the height of this particular bin, if x 1 falls within this bin, because that is our assumption that within a bin or within a cell the probability density is constant. Okay. So, this is one of the ways in which we can estimate the probability density function from a set of given samples. Now, to explain this further, we will take an example. Again, for simplicity, initially we will take an example for single variable, then we will extend this concept to vectors, to vector spaces, where I have multivariate probability density function. So, let us take an example. Suppose I have a variable x, where this x or the range of x is between say 0 and 10. So, the maximum value that x can take is 10 and the minimum value which x can assume is 0. So, I am assuming that I have the variable x can assume any value within the range 0 to 10, where both 0 and 10 are inclusive. And now, if I take a number of samples, so let us take a number of samples like this. So, suppose this is the set of samples which are given to estimate the value of p x, the probability density function for the variable x. So, you find that here I have a number of samples, the sampled values of x are 0, 1, 2, 2. So, 2 appears twice, because I can have 2 samples having the same values, then 2.5, then 3, 3.6, 3 again, 4, 5, 4, 7, 9, 9.2. So, the number of samples that I have is 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So, I have capital N, that is number of samples is equal to 14. And now, I want to estimate the probability density function. So, for that, as we have said earlier, that I will plot this x, and let us assume that as this x or the range of x between 0 to 10 will be divided into a number of cells, let us assume that every cell will be of equal width, and we start with a cell width to be equal to 2. Okay. So, this x, it will have a minimum value of 10, minimum value of 0 and maximum value of 10, and I am having cells of width 2. So, the cell boundaries will be 0, 2, 4, 6, 8 and 10. So, these are the cell boundaries that I have. And now, I have to find out that out of these samples, which sample falls in which of these bins. Okay. So, you find that 0, which is on the cell boundary, and we have assumed that if a sample falls on the cell boundary, then by convention we assume that the cell that particular sample will belong to the cell which is to the right hand side. So, this sample which is 0 will actually fall in this 0th bin, whose boundaries are 0 and 2. Similarly, this will also fall in this 0th bin, the sample value 1, that will also fall in this 0th bin. And if you go through this list, you find that there is no other sample which is falling within this 0th bin. So, the number of samples which falls in the 0th bin is equal to 2. Come to the next one, 2, 2, 2.5, 3, 3.6, 3 again. All these samples 2, 2, 2.5, 3, 3.6 and 3. All these samples, they fall under this bin having the bin boundaries 2 and 4. So, the number of samples which falls within this bin is 1, 2, 3, 4, 5 and 6. So, there are 6 samples which are falling within this bin. The next one, within the next bin having the bin boundaries at 4 and 6, I have samples 4, 5 and 4 again. So, there are 3 samples which are falling within this bin. Next, 7, this particular sample, the sample 7 falls within the bin having the bin boundaries 6 and 8. And the next two samples 9 and 9.2, these two samples fall in the bin having the bin boundaries 8 and 10. So, I have two samples falling in this bin. So, now if I compute the areas, you find that I call this to be A 0, area 0, this to be area 1, this to be area 2, this to be area 3 and this one having area 4. So, value of A 0 will be equal to the number of samples falling in this 0th bin is equal to 2 and I have total number of samples which is equal to 14. So, this area of this under the 0th bin will be equal to 2 by 14. Similarly, A 1 that will be equal to 6 by 14, A 2 will be 3 by 14, A 3 will be 7 by 14. Sorry, here I had only one sample, not 7 samples. So, it will be 1 by 14 and A 4 will be 2 by 14. And from this, now I can compute what is the probability density in different bins, because that is nothing but the area divided by width, and I have assumed that every bin has the same width is equal to 2. So, if I divide A 0 by 2, which is equal to width, I get what is the probability density estimate in the 0th bin. This divided by 2 gives me what is the probability density estimate in the first bin and so on. So, if I compute this, what I will have is say A 0 will have, this is my H 0, which is nothing but 2 by 14 into 2, that is 1 by 14. Similarly, this will be 6 by 14, 14 into 2, that will be the probability estimate of this. So, I will get a value something of this form. Over here it is 3. So, I get a value of this form. Here it is 1. So, I get a value of this form, and here it is 2 again. So, I get a value of this form. So, you find that given this set of samples and assuming that I have bin size equal to 2, where every bin is of same size, the probability density estimate is given by a piecewise constant approximation, which is this one. So, this is my probability density curve. Right. Now, if you are given a value of x, an unknown x, so I take any value, say x 1 is equal to say 4.5, and I have to find out what is p of x 1. So, here you find that x 1 whose value is 4.5, in which bin this x 1 falls. And if you look at this diagram, this bar graph, you find that this 4.5 actually falls in this bin. So, 4.5 will be somewhere over here. So, the probability of this x 1 is given by the height of this. So, which is nothing but 3 by 2 into 14. Okay. This area is 3 by 14. I have to divide this by 2 because width is 2. So, that gives me this height, which is nothing but the probability density so far as this particular bin is concerned. And as x 1 falls within this bin, so the probability estimate p of x 1 has to be equal to 3 by 2 into 14, which is nothing but 3 by 28. Okay. So, this is how I can estimate the probability density function for a variable from a given set of samples for that particular variable. Now, having done this, the other problem that one has to face is that what should be the width of the bins. Okay? And depending upon the width of the bins, the number of bins will be different, because I have a fixed range of the variable x, and in this example what we said is the minimum value of x is 0 and the maximum value of x is 10. So, if I reduce the bin width, say instead of taking the bin width to be equal to 2, if I reduce the bin width to 1, I will have more number of bins. On the other hand, from 2, if I increase the bin width to say 5, I will have only 2 bins, or say bin width say 4, I will have lesser number of bins. So, let us now try to see that if I vary the bin width, or if I vary the number of bins in which I want to divide the range of x, what effect it is going to have on the probability density estimate. So, I will take the same example and try it with different bin widths. So, first let us see that what will be the situation if I assume that bin width is equal to 1. Okay. So, this is x, this is where on the vertical axis I want to put the estimated probability density, which is p of x, and this is divided into bins of width 1. So, 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. So, here it is 0, here it is 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now, given these bins, let us see, and I take the same set of samples which I have taken for the earlier example, that is 0, 1, 2, 2, 2.5, 3, 3.6, 3 again, 4, 5, 4, 7, 9 and 9.2. Okay. So, given this set of samples, you find that this sample 0 falls within the first bin, okay, and this is the only sample which is which falls in this bin. So, the number of samples which are falling in this bin is equal to 1. Similarly, the next sample 1, that also falls in this bin. So, the number of samples falling in this bin is equal to 1. Then 2, which is on the boundary. So, I will assume that it falls in the next bin. So, the next bin contains 1, 2, 2 and 2.5. So, these are the samples which are contained in the next bin. So, next bin contains 3 samples. Then comes 3, 3.6 and 3 again. So, these are the 3 samples which are falling in the bin having the bin boundaries 3 and 4. So, I will have 3 samples over here again. Then 4 and 4, these are the 2 samples which are falling in this bin, 5 goes to the next bin. So, the number of samples that I have in this bin having bin boundaries 4 and 5 is equal to 2, whereas the bin having bin boundaries 5 and 6 contains this sample value of 5. So, this contains only one sample. This bin having bin boundaries 6 and 7, you find that no sample is falling in that particular bin. So, number of samples falling in this bin is equal to 0. This sample 7, it falls in the next bin having bin boundaries 7 and 8. So, the number of samples that I have over here is equal to 1. Again 8 and 9, this does not contain any sample. The next one 9 and 10, this contains 2 samples, one is 9, other one is 9.2. So, the number of samples that I have over here is equal to 2. So, naturally, given this sort of situation, and you find that here W j, that is the width of the bin, is equal to 1. So, what I will have is h j, that is height of the probability density function or the probability density estimate, will be simply is equal to n j by n, okay, where n is the total number of samples as we said before, and n j is the number of samples falling in that bin. So, if you follow this, you find that this one within this 0th bin, I will have a probability estimate which is nothing but 1 by 14, because only one sample is falling in this bin, and the total number of samples or capital N that I have, this is equal to 14. So, this will be 1 by 14, this will be 1 by 14 again, this will be 3 by 14, here it will be 3 by 14 again, here it will be 2 by 14, here it will be 1 by 14, here no sample is falling within this bin. So, value of n j is equal to 0, right. So, this is 0, here again I have one bin, only one sample, here again it is 0, here I have 2 samples. So, this is the kind of probability estimate that I will get against this. Okay. So, if I reduce the bin width or if I increase the number of bins, then the kind of situation that I have is as shown here. Now, let us see the reverse case. If I increase the bin width or reduce the number of bins, then what I will have. So, now let me assume that I have bin width or W j, which is equal to say 4, and that is same for all j. So, the situation that I have is something like this 0, 4, 8, and the next bin boundary is 12. So, I have only 3 bins, though my actual range of x is up to 10. So, on this axis I plot x, on this axis I plot p of x or the probability of x. And again I use the same set of samples for estimating the probability density function. Okay. So, these are the samples that I have. So, first I have to see that out of these samples, how many samples are falling within the bin 0 to 10. That means, the values of x which are greater than or equal to 0, but less than 4. And you find that all these samples, they have values greater than or equal to 0, but less than 4. So, I have 1, 2, 3, 4, 5, 6, 7, 8. 8 samples which are falling within this bin. Next, from 4 to 8. So, all the samples having values greater than or equal to 4, but less than 8, they will fall within this bin. So, here you find that I have these samples 4, 5, 4 and 7. So, 4 samples are falling within this bin, and the remaining 2, that is 9 and 9.2, these 2 samples, they are falling within this bin. So, if I use this, now we find that here W j is equal to 4. So, height of every bin H j will simply be N j by 4 times n, where this n is equal to 14. I have total 14 samples. So, for the first one, it will be 8 by 4 into 14. So, I will have something like this. For the next one, it will be 4 by 4 into 14. So, the probability density estimate will be something like this, and the next one will be 2 by 4 into 14. So, the probability density estimate will be something like this. So, if I use bin size of 2, then this is the probability density estimate. If I use bin size of 1, then this is the probability density estimate. If I use bin size of 4, then this is what is the probability density estimate. So, you find that in all these different cases, the probability density estimate that I get is different. Then the question comes that what should be the proper value of bin width, or what should be the proper number of bins? Because apparently it appears that this is what I should have from this given set of samples. If I use this, then this is overfit, right? Because if I have a sample unknown sample say x 1 which is equal to 6.3 and I compute this p of x 1, as this 6.3 falls within this bin for which the probability density estimate was 0. So, p of x 1 will always be equal to 0 as per this. So, this is an overfit given the set of samples. Whereas, if I use a larger bin size, that is the situation of this form, then what I am going for is I am going for more and more uniform density estimation. So, if the bin size is even larger, it will be more and more flat. So, as a result, the certain details in the probability density estimate as seen over here will be lost. So, the choice of the number of bins or the size of every bin should be such that the bin width is not too large. If I use too large bin width, I will lose the detailed information. On the other hand, if the bin width is too small or I have large number of bins, then it is quite possible that many of the bins will be empty. That is, none of the samples, the given samples will fall in many of the bins. As a result, the probability density estimate for those bins will be equal to 0. So, this bin width or the number of bins has to be properly chosen. But unfortunately, there is no analytical method of choosing the number of bins or the bin width. So, there is a thumb rule which says that if I have capital N number of samples, then the number of bins should be near about square root of n. This is just a thumb rule, but there is no analytical tools to decide what should be the number of bins for proper probability density estimation. Okay. So, this is the case that we have done in case of one dimension, that is assuming that our we have a single variable x and we want to estimate the probability density for that single variate case. But when you go for pattern recognition, earlier we have said that in case of pattern recognition, we normally do not deal with a single variable, but we deal with vectors which are called feature vectors, where every element in the feature vector gives some property of the pattern or some information of the pattern. And when I take all the information given by all the elements in the feature vector together, so all those information together gives me a representation of the pattern. So, in our case or similarly in many other applications, the probability density that we need to consider is not a single variable probability density, but it is a multivariate probability density. So, what we have to use is a multivariate probability density estimation. Okay. And let us see that how this probability density estimation technique for a single variable can be extended to multivariate, or if I have a vector space having multiple number of vectors having multiple number of elements, how this technique can be extended to multivariate case or in vector spaces. So, I will start with a simpler case where I assume that I have two dimensional feature vectors. That means, now this x, instead of being a single variable, it is a vector which I represent by capital X, and this vector has got two components. One I say x 1, the other one is x 2. So, this is the vector, and when I take different samples for estimating the probability density, what I will have is different sampled values of x, that is this vector, where every sample will have a corresponding sampled values of x 1 and a corresponding sample values of x 2. So, I will have different instances of this vector x 1 x 2. Now, find that unlike in case of one dimension, where this probability density function was a curve. So, this was my x, this was my p x. If I go for continuous probability density, I get a curve something like this, and if I go for this approximation, I have piecewise constant approximation of this probability density estimate, which is something like this. And so on, where effectively my probability density curve is this one. So, find that in one dimensional case, the probability density function is represented by a curve. So, in case of one dimension, this probability density function is represented by a curve. So, you find that if I extend this to two dimension, where I have two different axes, one axis representing this component variable x 1 and the other axis representing this component variable x 2. So, I have a two dimensional space or a plane. So, if I represent that by a coordinate system, I have this axis representing this component x 1 and I have this axis representing the component x 2. And any vector having a component value x 1 and a component value x 2. So, for example, if I take a vector say 3 5, this is a vector say x 1, it is equal to 3 5. So, this 3 5, this particular vector is nothing but a point in my two dimensional space or two dimensional plane defined by x 1 and x 2. So, this 3 5 is a vector or is a point somewhere over here. So, this is my point 3 5. So, every vector, every two dimensional vector is nothing but a point in this plane, which is defined by x 1 x 2. So, if I want to now find out what is p of x, that is the probability of vector x. So, thus p of x will be represented on an axis which is perpendicular to both x 1 and x 2. So, what I get is a three dimensional space x 1 x 2 representing the plane in which all the vectors will lie, and I have another dimension, another direction which is orthogonal to both x 1 and x 2, and that represents my p of x, where x is a vector. So, p of x for this particular case will be a point in three dimensions somewhere over here. Similarly, if I take a vector over here which is say x 2, or instead of calling them x, let me call them as y to avoid ambiguity. Okay. So, my vector is y whose components are x 1 x 2. So, this is a vector y 1, instead of calling it x 1, let us call it as a y 1. Similarly, if I have a vector y 2 over here, that will p of y 2 will be another point in this 3-dimensional space. So, if I join all these points in 3-dimensional space to represent my probability density function, you find that all these points define a surface in the 3-dimensional space. So, when I say the probability density function of a 2-dimensional vector, this probability density function is nothing but a surface in the 3-dimensional space. Whereas, in case of 2 dimension, in case of 1 dimension for a single variable, this probability density function is a curve in a 2-dimensional space. Okay. So, that is the difference. From curve we are coming to the surface. So, for probability density estimate, as in 1-dimensional case, we have divided the range of x into a number of bins of certain width. Okay. In the 2-dimensional case, I have two different variables, one is x 1, other one is x 2. These are the two components of my vector x. So, both x 1 and x 2, they will also have their ranges. So, x 1 will have a minimum value of x 1 and it will have a maximum value of x 1. Similarly, x 2 will also have a minimum value of x 2 and it will have a maximum value of x 2, which defines what is the range of x 1 and what is the range of x 2. So, once I have that, then this x 1 x 2 plane, let us put it like this. This is x 1, this is x 2. So, this is, let us assume that this is the maximum value of x 1 and this is the minimum value of x 1. So, it is 0 to maximum. Similarly, this is the minimum value of x 2 and this is somewhere over here we have the maximum value of x 2. So, which defines what is the range of x 2. So, if I divide this x 1 into a number of bins, as we have done in case of 1 dimension. Similarly, x 2 is also divided into a number of bins as we have done in 1 dimension. So, find that effectively what we are doing is this limited space, bounded space, which defines the range of x 1 x 2, because I cannot have any value of x 1 which is greater than this, I cannot have any value of x 2 which is greater than this, I cannot have any value of x 1 which is less than this, I cannot have any value of x 2 which is less than this. So, this defines a bounded space or bounded area. And when I break this x 1 and x 2 into a number of bins, effectively what I am doing is this bounded area is divided into a number of rectangular cells. Okay. So, the cells that I will have will be rectangular in nature, something of this form. So, these are the cells that I have, and you find that if I go to this 1 dimension, what the cells were linear in nature, or that one, yeah. So, these were the cells in 1 dimension which are linear or line segments, and the cells in 2 dimension, they will be rectangular cells or rectangular bins, something like this. So, as we have done in 1 dimension, here what I will do is, I will take a cell, say I jth cell, because it is in 2 dimension. So, I have to have 2 indices, unlike a single index in 1 dimensional case. So, I pick up an I jth cell, and as before, the total number of samples which are given for probability density estimation, if I assume is capital N, and out of this total number of samples, suppose n I j is the number of samples which are falling within this I jth bin. Okay. Then the probability density estimate of this will be given by n I j upon capital N. Okay. And you notice another point, that as I said, that in case of this two dimensional vector, the probability density function is given by a surface. So, if this surface representing the probability density function is an approximation of a continuous probability density, in that case the volume under this surface. So, you note the difference. In case of one dimension, I had a curve. So, I had considered the area under the curve. In this case, in two dimensional case, it is a surface. So, I have to consider the volume under this surface. So, suppose this is the surface and this is my xy plane. So, I have to find out that what is the volume between this surface and this xy plane. So, if this probability density estimate is an approximation of a continuous probability density function, then the volume under this surface, the surface which represents the probability density function, has to be equal to 1, right. Or in other words, what I must have is this sum of this has to be equal to 1, and which is obviously true, because n j is the number of samples out of this n which falls in the I jth bin, and this n is the total number of samples. So, if I simply sum them up over all I and j, that has to be equal to 1. Okay. Or this represents the volume, this has to represent the volume of the probability density function over this I jth bin. So, you find that in case of two dimension, the kind of estimate that we had over here. So, this represents an area, here this represents a volume. So, the probability density estimate, if this is my P of x, then over this I jth bin, the P of x will be given by a bar, something like this, where the volume of this bar is given by this n I j by n. And if the area of the base of this bar is a I j, then the height of this bar h I j will be given by n I j upon a I j times capital N. So, if you compare this with our one dimensional case, instead of this area a I j, what I had was the width of the bin w j. So, over here this is not the width, but it is the area of the bin I j. This is the area of the I jth bin, which is a I j. So, now it is a very simple extension of the probability density estimation technique from one dimension to two dimension. So, you have been given a large number of samples or capital N number of samples. I have to check that out of these capital N number of samples, how many samples are falling in the I jth bin, and if I know, or obviously I have to know that what is the area of the I jth bin, then the probability estimate or h I j will be given by n I j, that is the number of samples falling in the I jth bin, divided by capital N, that is total number of samples, divided by the area of the I jth bin, which is a I j. So, over here the height of this, which represents the probability density estimate within this bin, that is h I j, is simply equal to n I j upon a I j times capital N. So, this is a simple extension from our one dimensional case to a two dimensional case. Right. So, again to explain this further, to clarify this concept, again I will take an example to explain how this probability density estimation in two dimension will work. So, again let us take an example with a number of two dimensional feature vectors. So, I have a set of feature vectors. Let us assume that we have set of feature vectors 1 1, all are in two dimension, 1 3, 2 1, say 2 2, 2 4, 4 2, 4 3, 4 5, 5 4, and say 6 2. So, suppose these are the two dimensional feature vectors that we have, and using these two dimensional feature vectors I have to estimate the probability density function or p of x, where this x is a vector of the form x 1 x 2. Right. So, total number of sample vectors that I have is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So, my capital N or the total number of samples is equal to 10. So, what I will do is I will consider a two dimensional feature space having x 1 x 2 as two different axes. Okay. And here if you analyze, if you find out the values of x 1 and if you find out the values of x 2, here you find that I can easily say that the range of x 1 is between 0 and 10 and the range of x 2 is also between 0 and 10, because I do not have any value of x 1, the first component which is greater than 10 or less than 0. Similarly, for x 2 I do not have any component x 2 whose value is greater than 10 or less than 0. So, I can very easily assume that the range is between 0 and 10, here also the range is between 0 and 10. Right. And now, let us say that we have the bins, every bin is say of size 2 by 2. So, this x 1 will be divided into 5 bins, each of length 2, x 2 will also be divided into 5 bins, each of length 2. Okay. So, suppose these are the bins. So, once I do this, effectively what I am doing is I am dividing this space into 5 into 5, that is 25 rectangular bins. So, these are the bins in the two dimensional space I have. Now, let us try to see that out of these given samples, which sample is falling in which bin. So, if you look at the first one, this is 1 1, 1 1 is falling, 1 1 is nothing but, because this is of size 2. So, this is 2, 4, 6, 8 and 10, 2, 4, 6, 8 and 10. So, 1 1 is a point somewhere over here. So, it is falling within this bin. 1 3 is a point somewhere over here. So, which is falling within this bin. Similarly, 2 1 is a point somewhere over here. So, it is falling within this bin. 2 2 is this point, but by convention, as we said, that we assume that this falls within this bin. 2 4 okay. Again that is this point, and by convention we assume that this falls on this bin. 4 2, which is this, by convention we take that it falls within this bin. 4 3 is somewhere over here, by convention I assume that it falls within this bin. 4 5 is somewhere over here, by convention I assume that it falls within this bin. 5 4 by convention I assume it falls in this bin. Then 6 2, it is this point, I assume it falls in this bin. So, you find that here I have only one sample, here I have only one sample, one sample, one sample, one sample, here I have two samples, I have two samples, I have one sample over here. So, the volume of the bar over this, if I take this particular one, volume of the bar V I j will be equal to 2 by, I have total number of samples which is equal to 10, and height of this bar H I j, which will be simply this divided by area of the base, and this being a bin of size 2 by 2, area of the base is equal to 4. So, H I j will be equal to 2 by 4 into 10, and that is nothing but the probability density estimate within this bin. Okay. So, now you find that if I have x 1 which is equal to, let us say 5 5. So, 5 5 falls within this particular bin. So, P of x 1 is nothing but this H I j, which is 2 by 4 into 10. So, you find that we have simply extended the concept of probability density estimate from one dimension to two dimension. Okay. I will continue with this further in our next lecture. Thank you.